Hello, I'm David Ruzick, Illinois Energy Prof. And today I'm going to talk about the uranium supply chain. So the first thing you might imagine one has to do is dig up the uranium ore. That's not enough, because to be able to enrich it, you have to turn it into a gas. And that process is called conversion. Once it's converted to a gas, you can improve and increase the amount of uranium-235, and we call that enrichment. And then finally, you're going to have to make fuel out of it, and we call that fabrication. Today, I'm going to walk you through all of these steps. All right. Let's talk about supply. The picture in the upper corner is a map of the world, and the darker the country is, the more it has. You can see Australia by far has the largest supply of uranium ore. And then we go on to Kazakhstan, Canada, Namibia, Russia. If we add this all up, it's 6 million tons of ore, and we only use about 70,000 per year. You might say, well, that's not enough years, or what happens if we use a lot more nuclear power? Well, that's fine. This is the cost at $130 per kilogram. If you're willing to pay more, then there are other sources, other mines that become more economic. And like any type of resource, you never run out. You just can never afford to buy the last bit, because the price goes up and the supply goes up. If you have all of this ore, you still have to mine it. You still have to put it into production. And even though Australia has the largest supply, it actually does not have all that much uranium mining. And so clearly one thing to extend nuclear power into the future, powered by uranium-235, is mining in Australia. At the moment, uranium ore is a commodity. Anyone can buy from anywhere. Clearly it makes sense to buy from something that's closer because you have to ship it. So the US tends to get their ore from Canada, and Russia and China from Kazakhstan, because again, those are closer to them. But until we have other tensions in the world or a lack of free trade, which is always a concern, you can buy the ore. Now, having the ore is not enough, because you need to convert it, right? The ore is a solid. And I can't take a solid through the type of plant that's enabling us to enrich the part of the uranium we want, the uranium-238. So we have to turn this solid into a gas. And that process is called conversion. And it's specialized, and it's done in large chemical processing plants. All right, so where do they do this? Well, there's 5 places in the world. And as you might imagine, they're at the places that either have the supply or the places that use nuclear power a lot. Canada, China, the United States, France, and Russia. And what exactly do? They get in this solid ore, take out the uranium-238 and 235 all at once in the form of U3O8, it's the yellow cake. Then they're going to add hydrogen gas at a high temperature, converts it into a product. The next step is to use a very strong acid, hydrogen fluoride, HF. And then finally, a step where they add fluorine gas. And that will end us up at uranium hexafluoride, a gas. Metropolis, Illinois, here in the state of Illinois, is the place in the United States that this is done. And fun fact, Metropolis, Illinois also happens to be the home of the largest Superman statue. So now we get to the step that everyone has heard of, enrichment facilities. You see, uranium is only 0.7% uranium-235. This is the stuff that's your fuel. This is the stuff that can fission with any energy neutron. And that means it's 99.3% uranium-238. Just kind of comes along for the ride. To make something useful, like a nuclear reactor, this number has to go up. To make some of these newer nuclear reactors, it has to go up even more. And if you really wanted to make a nuclear weapon out of that, it needs to be almost all greater than 90% U-235. And whenever you do one of these enrichment steps, say I take that 0.7%, I'm going to end up both with enriched uranium and depleted, right? Because the uranium-238 doesn't go away. What happens instead is that I might get a small amount of this, right? And I'll have a large amount of this. That in the end, perhaps this is for reactor, this is 3.5% U-235, and this is 0.2, not 7 anymore, but 2% U-235. Uranium is a relatively common element, much more common than silver, for instance, about the same plentifulness in the Earth's crust as tin. Now, where do they do this enrichment? There are a number of places, and again, you might imagine it's in the countries that are using nuclear power to a much larger extent. There's 4 in China, 3 in Russia, 4 across Europe, and 2 in the United States. The big one that we've had for a long time is in New Mexico, and recently they have been qualified to enrich the fuel up to 10%. If you saw my previous video, the type of fuel we plan to use in the microreactor at Illinois is that type of fuel, 9.9% uranium-235. The Ohio facility, which has opened recently, is actually making fuel that's called HALEU fuel, and that fuel can be up to 19.4% uranium-235. All right, so how is it done? Well, the old way to do it, the way that was done in the 1940s, say for the Manhattan Project, was gaseous diffusion. The way this works is that if I have uranium-235 F6, the weight of this, the atomic weight, is 349, 6 times 19 plus 235. Where U-238 F6, that mass is 3 mass units higher, 352. And if something is less massive, it diffuses faster. The ratio is compared to the square root of the mass number. So this goes as 1 over the square root of the atomic mass. And the square root of these two numbers is not very different. This improvement factor for one cycle is only 1.0043 for each step. Meaning if I start with this 0.7% U-235, in one step I get a slightly enriched gas at 0.703% and a de-enriched gas at 0.697%. Then I'm going to have to take this gas, put it through the diffusion process again, and get slightly higher, and again have some stuff that's actually back to 0.7, and you have a whole chain of this diffusion plants. In Oak Ridge, where they did this the first time, they needed the entire TVA power plant dams to make the electricity to run enormous gaseous diffusion to be able to get enough enriched uranium for a couple bombs. So this process, this takes maybe 400, on the order of 400 steps. There has to be a better way, and in fact, there is. The entire world right now enriches uranium using a gaseous centrifuge. Not worked on the principle of diffusion, but rather that if I spin something around, the heavier atoms spin out farther. They separate. And if I suck off gas from the edge of the centrifuge, I suck off the heavier component. If I take away the gas from the middle of the centrifuge, I take away the lighter component. And each of these steps of improvement, instead of 1.043, is 1.2. Much better. And here in this enrichment, instead of going from 0.7% to 0.703, right, we can actually go to 0.84, meaning the de-enriched part is 0.56. A tremendous more improvement in each step. You still need a multi-step system, and therefore, as you see in the picture, rows and rows and rows of these very high spinning centrifuges. And if I do this, I can get it not from 400 steps to around 10 steps. Vast improvement in the ability to enrich uranium. And of course, this 1.2 factor depends on the speed of your centrifuge. So as technology increases and you can make something even faster, you might be able to do it just a little more efficiently as well. So, can this be done even better? Maybe. I'm actually working with a company, laser isotope separation, that is trying to do this. And the idea is not to utilize the mass, but to use the spectra, the photons that would excite a molecule or not, the photons that a molecule gives out. And the way you would try to do this is you would use a laser tuned to one of those frequencies. And if this all worked out, you might have a single step enrichment factor of 5. You could go from this regular ore to reactor fuel in one step. But remember, I said maybe. So what is this stuff about frequency and so forth? Well, you got a molecule, right? We've got uranium, and it's got 6 fluorines connected to it. It's not all flat, right? That's 5, we got 6, so it's like a ball. And this whole thing can rotate. You might say, oh, so what? Yeah, I can spin it. I could see it tumbling in space. Okay, it can rotate. But when I say rotate, everything is quantitized. So it doesn't just rotate at any old speed. It can only rotate at certain speeds. The other thing is it can vibrate, right? The fluorines can come out, they can go back in, they can come out, they can go back in. And again, there's only specific energies that happens at. So you see a spectra here, and you'll see these peaks, right? You've got something like this, and then a big one, and then something like this, and a big one again. These are the vibrational states, all right? And these are the energies of the rotational states. Now, if this was U238F6, let me get a different color here and show you what the spectrum might look like for U230, the green one, U235F6. And maybe somewhere you can find a spot where if I had a laser that was exactly at that energy, it could pump up one of the isotopes and not the other one. That's the secret and the thing you want to do with a laser. You want to be able to excite one of the isotopes and not the other. A couple schematic drawings there. You can imagine a gaseous stream of the unenriched UF6 gas. The laser hits it, and only one of the molecules, the one that the laser light is tuned to, this particular line, this gets excited. If it gets excited, I can now do something different with them, and I could separate them. Has this been done before? Yes, but never at scale and never economically. And this is a way, however, that could make this entire enrichment process much easier, much faster, and much more affordable. All right, so now we have enriched gaseous UF6, but you still don't have fuel to put in the reactor. You have to fabricate it. We have to go backwards. We have to go back from the UF6, now enriched, gas. We have to get to a solid fuel pellet. So the first step is, again, a big chemical plant, and you react this with water at a high temperature and pressure, and you're able to turn this into an intermediate substance, uranium oxyfluoride, U2OF2. Another reaction from that, and by adding hydrogen to take off more of the fluorines, or water, depending on whether you want just UO2 or you want U3O8 again. These are back to being solids. And now you can pack those solids into fuel pellets or tiny fuel grains that become the heart of TRISO fuel, or any other form of the fuel that you want. We now have enriched reactor fuel. Who does this? There are companies, international companies, operate across borders. There's ones in the US, ones that operate in Europe. Clearly Russia and China have their own state-owned ones. South Korea and Japan also have fuel fabrication. So, in conclusion, we need to strengthen the supply chain, especially in the conversion and enrichment areas. But fortunately, the US is already doing this in a program that was started in the Biden administration that is continuing in the Trump administration. $2.7 billion is being put into these steps of conversion and enrichment because we expect more nuclear fuel to be needed as more nuclear power is produced in the United States, and similar programs are taking place in the rest of the world. So that is what you need to know about the uranium supply chain.